Hi, in this slice of physics we're going to take an energy conservation example. We're going to look at a child sliding down a backyard slide, discuss the energy transformations that are taking place, and use energy conservation to determine the change in thermal energy. Our question states that a 10 kilogram child slides down a 4-meter high backyard slide. She starts from rest at the top and attains a speed of 2 meters per second at the bottom. And then it's asking us what energy transformations are taking place, and then telling us to use conservation of energy to determine the increase in thermal energy of the slide and her pants. Okay, so let's draw a picture as usual to start. So here's my backyard slide. It's given to us that it's 4 meters high. The child is initially sitting at the top, and the child has a mass of 10 kilograms. My initial speed is 0, and by the time I get to the bottom, my VF is 2 meters per second. Okay, have I captured all the information from the question? I believe so. So let's get started. So in terms of energy transformations, the second question has some hints to answer the first question. It's indicating that this is not a frictionless surface, so we don't have a situation where there is no thermal energy that's being created. It's asking us to determine how much our pants and the slide get hot. So we do have some frictional forces acting here, and we have to consider thermal energy. So what energy is the child losing as she comes down? Well, she's going from a higher place to a lower place, so we know that potential energy is being lost, so that's what is the source of the energy. And because energy is conserved, the question says that, where is it going to? Well, some of it is going to the fact that she's getting faster. She started at rest and got to a speed of 2 meters per second, but that's not all of it. We are also told that there is thermal energy being created because of the heat, so we have this situation. Potential energy is converted to kinetic energy and thermal energy. Next, because we're going to use conservation of energy, we got to be careful in defining the system as something where there is no external work being done. The frictional force moves as the child moves, so the frictional force does work. So in order for us to have work external equal to 0 to use energy conservation, we got to define the system as something where all the forces that we are considering are internal forces. So if we define the system as the child plus the earth, remember the earth is needed to be included to consider potential energy, plus the slide. Now all of the forces are internal forces. The earth applies a force on the child and vice versa. The slide applies a frictional force on the child, and that's got an equal and opposite pair. So all of the forces now will be internal. So if I define the system as these three things, my external force is 0, and therefore my external work is 0, and hence I can use energy conservation. So because external work is 0, that tells me that change in total energy is 0, and in this case I got 3 energy components I got to deal with, so I can set up Ui plus Ki plus E thermal I equals UF plus KF plus E thermal F. I can rearrange this to get UF minus UI, KF minus KI, and E thermal F minus E thermal I. So I can write this as change in potential energy plus change in kinetic energy plus the change in thermal energy is 0. That's what we mean by saying the total change in energy is 0. Okay, now it's a matter of figuring out which ones of these we know and which ones we need to determine. So let's start with change in potential energy. That's UF minus UI. And if I set my 0 potential energy as the ground level, my final potential energy is 0. The child is at the ground. The initial potential energy is M times G times HI, which will give me minus 10 times 9.8 times 4.0, and that gives me minus 390 joules. Next, let's do delta K. We know the initial and final speeds, so we should be able to do delta K. Delta K is Kf minus Ki, and so that will be 1/2 mvf squared minus 1/2 mvi squared, which will be 1/2 times 10 times 2.0 squared, minus this whole term will be 0 because my Vi is 0, and this turns out to be 20 joules. It's a positive 20 joules because kinetic energy is increasing. So the child loses 390 joules of potential energy and only gains 20 joules of kinetic energy. Where's the rest of the energy going? Well, that's what's going to thermal. So going back to this equation, I got minus 390 joules for the change in potential energy, plus 20 joules for the change in kinetic energy, plus the change in thermal energy, and all of that has to equal 0 because energy is conserved for our system. And rearranging this, I get change in thermal energy is 390 minus 20, which is 370. The units were joules. So in sliding down, the child loses 390 joules of potential energy, 20 of which goes to kinetic energy, and the remaining 370 goes to heating up the slide and her pants due to the force of friction. So hopefully this example gave you an appreciation for the power of conservation of energy as a tool to solve certain problems in physics. But in doing so, we got to pay attention to what energy transformations are taking place and understand them, and be careful in defining our system such that there is no external work being done on it. Thanks for watching.